There are all kinds of differential equations that have different techniques for solving them. The differential equations class would go through several of those techniques. We're going to finish off this quarter by just looking at one, sort of the basic technique of how do you solve some of the simplest differential equations. And these are called separable differential equations. And so, definition, a differential equation is called separable if it can be written in a certain way. A diff EQ is separable some function of x times dx equals some other function of y times dy. Okay. There's a lot of ways that this could be written, but this is generally probably the simplest way to write this. Let me start with an example and say solve the following differential equation. So I'll explain how to solve it as I'm explaining this whole process here. So anyway, solve this differential equation. dy dx equals minus x over y. And we'll give an initial condition so that the solution contains the point 3, 4. Okay. So, what I'm going to do, this is separable because if I multiply, let's say, both sides by y, I've got y times dy dx equals minus x, and I multiply both sides by dx, I've got y dy equals minus x dx. Right? So what I've done is I've separated it. And this is the thing here, that one side of the equation just has x's on it, the other side of the equation just has y's on it. Some function of x times dx, some function of y times dy. And that's what I have here, although I've got them on the other sides of the equation, but that doesn't matter. I've got a function of y times dy and another function of x times dx. So once you've done that, then what we're going to do is integrate both sides. So I'm going to do the integral of the left-hand side. It should equal the integral of the right-hand side. If you do the same thing to equal things, you should get equal answers, right? Well, actually not entirely in this case, because it's possible to have, I mean, you're taking antiderivatives, right? To do these integrals, you're essentially taking antiderivatives. And there's more than one antiderivative. So it may not be that these two sides are equal to each other, but if they're any different at all, it will just be plus a constant. So I'm going to have to remember when I get done. I'll integrate this, I'll integrate that. I got to throw a plus a constant on one side to make sure that they are equal to each other. Okay. Anyway, the integral of y dy is y squared over 2 plus a constant. The integral here is minus x squared over 2 plus a constant. I'm going to claim that I only need the plus a constant on one side. Because if you had a constant over here and a constant over there, then just subtract this one off. You have a constant minus a constant. Well, that would still be constant. So here we go. So now I'm going to actually multiply both sides by 2. So I've got y squared equals minus x squared plus, well, 2 times a constant. But 2 times a constant is still constant. And then I'll add the x squared over here. So I've got x squared plus y squared equals a constant. In fact, I think this was one of the examples we used in my first video about differential equations. Dy dx is minus y over x. And I just said, hey, look, this is the solution. Well, here's how you show it's the solution. That we actually separate the equation, integrate both sides, and we've got it. It's not always the case that you can separate it. Sometimes it's just impossible to get all the x's separated from the y's, or even if you do get them separated, you might have a plus x over here that's not being multiplied by the dx. Right? Everything, the way this is set up, everything, that whole function of x has to be multiplied by the dx, and the whole function of y has to be multiplied by the dy. If you can write it like this, then integrate both sides, and you've gotten rid of the dx and the dy now, and you can solve for the function. Sometimes this solves nicely. In this case, it doesn't. If I did solve for y, I'd have to take a plus or minus square root, and I'm not getting a function out of that. So I'm inclined to leave this as a relation. But there's one more piece I got to do because I wanted this initial condition. I wanted it to pass through the point 3, 4. So that's telling me to plug 3 for x and 4 for y and figure out what value of c I need. Well, this would be 9 plus 25. Sorry, 9 plus 16 is 25. 9 plus 16 equals c, so c equals 25. And my particular, this is like the general solution. This gives you all the different solutions. The particular solution that passes through the point I wanted is x squared plus y squared equals 25. Okay. The method of separable differential equations is to separate it, get all the x's on one side, all the y's on the other side, and then integrate both sides. Now, before I go any further, I want to state that I'm pulling a little bit of wool over your eyes, and that I remember as a student being sheepish about this. I was very much aware of how algebra worked, and it's like, yes, if you have two things that are equal to each other and you do the same thing to them, then you'll get equal answers. But I never felt like I was doing the same thing. That this right here, this is an integral with respect to y, this is an integral with respect to x. Why on earth should those actually be equal to each other? Well, really what's happening here is that at this stage right here, integrate both sides with respect to x. So this is y dy dx equals minus, or the integral of minus x dx. That at this stage you're you're integrating both sides with respect to x. Now, this is like what we did with u substitutions, that dy dx times dx is just dy. So this thing here is equal to the integral of y dy, which is now also equal to the integral of minus x dx. Right? So although it looks like you're integrating one side with respect to y and one side with respect to x, actually back at this level, you are integrating both sides with respect to x, and it just turns out to look like you're doing one with respect to y and one with respect to x. Okay? So that makes me feel a little better that we really are doing the same thing to both sides. Okay? Let's do another example. This is one, this was the population growth model, where the derivative of y is equal to some constant times y. This is separable because I can divide both sides by y, so 1 over y, instead of y prime, I'll write it as dy dx equals a constant, and then you can multiply both sides by the dx. So 1 over y dy equals k times dx. Okay. And sometimes it seems a little weird because there aren't even any x's over here, but, well, a constant is still a function of x. It's just the constant function of x. So integrate both sides here. When I integrate 1 over y dy, I get the natural log of the absolute value of y plus c, but I'm going to hang on to the plus c until I get it over here. Constant times dx integrates to a constant times x plus another constant. Now, if I exponentiate both sides, see, in this case, I feel okay with solving for y because I'm not doing something that's not really it's when I'm inverting something that's not invertible that I have issues. But natural log and exponentiation are inverses of each other. So I'm going to do the e to the natural log of that and e to the natural log of this. So this just gives me the absolute value of y, and this is e to the kx plus c. Now I'm going to do a little bit of monkey business here, but it's legal monkey business. That this, I claim, is equal to this. That usually we go the other way. When we have two things multiplied together with the same base, you add the exponents. Or if I have something with added exponents, I could write it as a product there. But e to a constant power is just a constant. So I can write here y equals constant times e to the kx. Notice, I lost the absolute value sign. And I did that legally because e to a constant, whether c is positive or negative, e to that power is positive, forcing this right-hand side to always be positive, hence the absolute values. But when I write this just as a c, I allow c to be either positive or negative. That allows y to be either positive or negative, and I don't need the absolute values around it anymore. Okay. Anyway, we started off with the derivative of y is equal to, where was it? I'm going to write it down again here. We started off with y prime equals k times y, and we ended up with y equals this exponential function. Okay. That's exponential growth. Do I have time for one more? I do. Let's do one more. How about something just like dy dx equals, just x times y. If I divide both sides by y, this is going to be a lot like the last one, and I multiply both sides by x, then I've got 1 over y dy equals x. I multiply both sides by dx. So 1 over y dy equals x dx. Integrate both sides. Natural log of y here, natural log of the value of y, equals x squared over 2 plus a constant. Solve for the y by exponentiating. Absolute value of y equals e to the x squared over 2 plus c. I'm going to do that same thing and write this as e to the x squared over 2 plus, not plus, that's the point here, times e to the c. But now that e to the c is a constant, it's a positive constant, but I can rewrite it as c e to the x squared over 2, which allows c to be positive or negative, which then allows me to drop that absolute value sign. Okay. So there's separable differential equations. Not everyone can be, but if you can multiply and divide stuff across so that you end up with a function of x times dx equals some other function of y times dy, if you get it that way, then integrate both sides, solve for y. Okay. Now, in this section, there's a bunch of applications which I am not going to worry about this quarter. So learn how to do some of these when you're working the problems from the homework. You can stop at maybe 25. When you start getting the applications, they do these things called orthogonal trajectories. They do some mixture problems. It's all described in the text, but I think just for this introduction here, I think just getting the idea that, hey, I can solve some of these differential equations, I think is enough for us to do for now. Okay. So anyway, there you go. If you have any questions, please ask them in the forum. Come talk to me in my office. And this is the last thing we're going to do this quarter.